recording.
Yeah. Okay. So at some point I might turn my camera off and pace around because I like to do that sometimes, but we'll see.
Okay.
So yeah. So yeah, there's a real kind of disadvantage of not being able to like stand in front of people. Um, so yeah, hello everyone. I'm Jameson. I'm a third-year student in the CMT. I work with Marin Saliacic, and the topic I'm here to discuss today, broadly speaking, is about modern light matter interactions, and specifically, I'm going to be focusing on looking at things from a sort of quantum mechanical perspective. That's the ultimate goal. So the first statement or kind of claim I want to make is that light matter interactions form the foundations for a very wide variety of physical processes that are important both technologically and for foundational physics. And in terms of forces, electromagnetism is, very largely responsible for, the way that matter works, the way that chemical reactions occur, the stability and structure of atoms and how they interact with each other. So, light matter interactions, in some sense, most of the world we experience consists of either light or matter. So my claim is that this is thus an important subject. And just some examples from a quantum mechanical standpoint, you have something like spontaneous emission of quantized energy levels of an atom, where a atom goes from an excited state to a ground state, emitting a photon in the process. And this photon is, a single countable quantum object. There's things in sort of like relativistic quantum electrodynamics, like the Lamb shift, where you can calculate how the energy levels of hydrogen will shift just ever so slightly as a result of vacuum fluctuations of the electromagnetic field. Not a quantum thing, but synchrotron sources of light use highly relativistically accelerated electrons to generate pulses of high frequency radiation like X-rays. And then from like 1960 onward, you have something, you have the invention of the laser, which is an extremely important source of monochromatic and stable coherent light. And then, in the 60s and 70s onward, you have the generation of things like entangled photon pairs and being able to do essentially quantum optics, where there's a, quantum aspect to the photon as well. So this, this encompasses a very broad, or light matter interactions encompasses a very broad series of subjects, and here's some examples of books ranging from the electrodynamics aspect to the quantum light matter interactions, all the way to like relativistic quantum field theory, quantum optics, and then also nano optics. So the question I sort of want to pose is, we've seen all of these, I've pointed out all of these important developments, and the question I want to pose is sort of like, what has the last 30 or 40 years brought to light matter interactions, and where are we going from here? So there are two main things that I want to point out. The first is that in the absence of material, so before I point out the two things, I want to comment that without materials, photons are pretty boring. So all of these aspects of light matter interactions, like scattering, spontaneous emission, the Lamb shift, all of these kinds of things, if you take a quantum field theory class or like an AMO class, typically you would calculate quantities in the presence of the vacuum electromagnetic field. So you just have empty space. Maybe you have an index of refraction, but in a lot of cases, probably not. And in this case, the dispersion of the photon is linear. And generally speaking, life is pretty simple. And so the focus of this talk will largely be on what happens when we deviate from those kinds of assumptions. The first way we can deviate from that is with developments in new materials, like two-dimensional materials and others, composite materials, heterostructures. Essentially, by changing material, by using interesting new materials, the way that light matter interactions works at a fundamental level will be changed. And so that'll be a big subject of discussion. And then something that goes hand in hand with this is the ability to fabricate things at length scales which are comparable to the wavelength of light itself. So if you're thinking about the way that Maxwell's equations works in a system of lenses and mirrors, then life is pretty simple because all of the objects you're thinking about are way bigger than the wavelength of any light involved, and as a result, something like ray optics works very well. And so you don't actually have to solve Maxwell's equations to know how light bounces off a mirror or to describe how it propagates through a lens. You can just draw a bunch of arrows. On the flip side, if the scales are kind of near each other, and now we're able to, through photolithography, electron beam lithography, make these sorts of remarkable structures that have features with, micron or nanometric size. In this case, thinking about the actual solutions to Maxwell's equations will be a critical component of understanding how light propagates in materials like this. And so what I want to do now is present a sort of framework for thinking about how both materials in terms of their fundamental properties like conductivity or their permittivity, as well as physical structuring and patterning can come together in order to create highly versatile platforms for controlling both classical and quantum electromagnetism and their interactions. So a way to think about this, and the kind of fundamental point of this slide, is that at a microscopic level, we have materials which are composed of charges and bonds between those charges, and this is kind of like solid state physics land. And depending on the way that microscopically a material behaves, you can deduce what its macroscopic response functions are, as characterized through its electric permittivity or magnetic susceptibility, or its conductivity, depending on how you want to cast it. And so, condensed matter physics, I think, there's a lot of emphasis on how, things like the electronic band structure, the phonon spectrum, et cetera, can interplay together in order to determine what the kind of bulk electromagnetic properties of the material are. So that's kind of the first aspect. And then the second aspect is that once we have a material, we can pattern or structure it in some way. And then the combination of those two things leads to the solutions of Maxwell's equations, or effectively what the photons are in that electromagnetic environment. And we can refer to this as like a photonic quasi-particle. So whether it be a free space photon, a photon in a block of silicon, a photon in a periodic medium, a photon in a cavity, or some kind of surface excitation on like a metal, the end result is the same, which is that all of these objects are photon-like objects, which can then proceed to interact with matter through quantum electrodynamics. So I'm going to talk about sort of two families of examples of these kinds of things, just to give some context, and then I'm going to be referring back to them later as well. The first is photonic crystals, in which you take some material, like silicon is a good example, which has a pretty high bulk index of refraction, and then you pattern it in some way to be periodic in 1, 2, or 3 dimensions. And as a result of this patterning, the solutions to Maxwell's equations in such a material will take on the characteristics of basically, the way that block waves work very similarly to an electronic structure theory. So you have some kind of block phase, and then you have some kind of periodic envelope function, and then the wave vector of excitations in this material are restricted to be in a Brillouin zone that's commensurate with whatever the periodic structure of the photonic crystal is. And what this means is that the band structure, the photonic band structure of the photonic crystal will be different than that of a, say, uniform medium of vacuum or a uniform medium of silicon. It's somewhere in between, and the way the periodicity works affects the band structure. So then this leads to things like photonic band gaps, for instance, where there are frequencies at which no wave vectors are solutions inside the material. So you get cool behaviors like a photonic crystal with a band gap. You send light at that frequency at it, and it just bounces off, giving you basically 100% reflection as mediated by constructive interference of the block modes of the wave that's trying to get in there, but it can't because there are no propagating solutions. And then this one at the top is an example of a photonic crystal cavity. So there's some hexagonal lattice, and then and then there's a missing element in the middle. And so essentially there's some highly confined single spatial mode that kind of lives spatially localized to the inside of this cavity. And then this one on the bottom left is like a wood pile, what they call a wood pile structure. Again, and you can measure the optical properties. So photonic crystals are one example. Photonic crystals in cavities are one example of how you can spatially modify a kind of everyday material like silicon in order to create electromagnetic modes which are quite different than they would be normally. So the dispersion is quite different. Another example is what happens at surfaces which contain potentially highly confined evanescent surface waves. So a surface plasmon is an excitation which lives at the interface of some kind of metal and then maybe a dielectric on the other side. And because of the negative value of the permittivity, if you solve for the dispersion, you'll find that there are these basically waves that are confined to the surface, and moreover, their dispersion relation is different than the dispersion relation of the bulk silicon substrate, and which means that they're further along in the wave vector direction, so they have wavelengths that are shorter than the wave would be in free space. And this is something we refer to as confinement. A much stronger limit of this is observed in a system like graphene plasmons, where you have a sheet of graphene at an interface between two dielectrics, and then the charge density in the graphene can oscillate along with the evanescent electromagnetic field, and you can end up with graphene plasmons, which are quite sub-wavelength. Now, it turns out that these are just one of many examples of these kinds of 2D excitations in van der Waals materials. So graphene plasmons are one example, and in that case, there's this hybrid excitation between light and matter, where on one hand you have the oscillating charge density in the graphene, and on the other hand you have this electromagnetic field that's carried along with the charge density. And broadly speaking, these are referred to as polaritons, which is sort of a hybrid excitation between light and matter. And from for the plasmon example, the charge density oscillation of the matter and the electromagnetic field wave that's propagating along with it, these are essentially one and the same. And if you know a response function like the conductivity or the permittivity, then you can solve Maxwell's equations to find these waves more generally. Another example of a kind of microscopic behavior which can lead to confined electromagnetic waves propagating on a surface is something like phonon polaritons at optical frequencies in hexagonal boron nitride, or silicon carbide is another example. And instead of a charge density oscillation like with a plasmon, the picture you want to think about here is that you have some optical phonon in the material, which means that the lattice vibrates. Moreover, it's an optical phonon because the unit cell of the material has a dipole moment. So as the phonon vibrates, there's also a dipole moment that propagates in the material. And with this, there's an electromagnetic wave that is carried. And then, one final example is something like magnon polaritons, where you have a spin density oscillation in some kind of magnetic material, and then as a result, you have a highly confined magnetic wave that propagates along with the precession of the spin density in the material. Now, why do we care about these kind of things? One reason, as I mentioned earlier, is that these excitations can achieve very strong confinements of the wavelength, again, meaning that the wavelength is much smaller than the wavelength of something at a similar frequency in like a, in a vacuum, for instance. So this column on the left that's highlighted for a bunch of different flavors of surface polaritons is the confinement factor, which tells you about that level of sub-wavelengthness. And then the thing you're fighting against here in any of these systems is loss, as characterized by the propagation quality factor. In other words, how many wavelengths the thing is going to propagate before it gets absorbed through some kind of, electron or phonon scattering process. The details of loss will depend on the microscopic mechanisms that are present within that material. but people are very interested due to the subwavelength nature, and also the ability to do something like, create new dispersions that are engineered. So this is an example of a dispersion relation of some kind of sandwich made with graphene and hexagonal boron nitride. The graphene has a plasmonic type behavior, and then the boron nitride has a phonon polariton type resonance. And they're able to overlap these in frequency ranges to get a rich variety of both plasmon, phonon, and hybridized modes. And something cool about this is that, with something like graphene, you can electrically gate it to tune it. And so people are very interested in these materials broadly as platforms, which can, be used to create, dispersion relations, which can be tuned dynamically, potentially in place by electrical gating. And this sub-wavelength, highly confined nature is something that's going to be important later on in the talk. So maybe just keep that in mind. And then we can think about different ways that both classical or quantum electromagnetic processes can potentially interface with something like surface polaritons. So you can have nonlinear processes, you can couple them in with a grating, you can shoot an electron beam at the thing to act as a current source. Or you can have something like a quantum dot near the surface, which then spontaneously decays into these surface modes. And in order to understand kind of all of these processes, either with polaritons or any kind of general material that we'd want to think about, even if it's not a 2D surface, this is just a good example. What we want to be able to think about is, how Maxwell's equations work in this system, and then also what quantum electrodynamics looks like in a system like this. So I'm going to have one slide on the classical aspect and another slide on the quantum aspect. From the classical point of view, we can write down Maxwell's equations in a material which is, for example, characterized by epsilon of omega and r here. So this is the dielectric permittivity, which is both a function of position r and also potentially a function of frequency, meaning that dispersion is present. Or in other words, different frequencies will behave differently in the material. And so epsilon of r and omega can encode a lot of information. This basically says, I could take graphene, hexagonal boron nitride, and then even, structure or pattern it in some way spatially. And so this, encodes everything about the material or composite material system that I want to think about. So there are two main approaches that we can take in formulating Maxwell's equation and solving Maxwell's equations. And both of these will be important from the quantum perspective too. One of them is a mode expansion method where you write down something like, where you look for basically eigenmodes of this double curl operator for the vector potential. And then this vector potential operator can be expanded in terms of these eigenmodes, which are F. And this works really well in a system which does not have very much dispersion or loss with it. So something like a photonic crystal made of silicon, for example, is great for this. However, a technical point is that in a material which has dispersion and loss, things get a little bit more complicated because you lose things like hermeticity of operators and realness of eigenvalues. And as a result, you cannot form a complete basis for the space of solutions to Maxwell's equations using an eigenmode expansion. Instead, what you have to do here, if you're working in like a plasmonic system where loss is very important, you have to use a Green's function formalism, where I basically look for these dyadic Green's functions, which dyadic means in this case that there are just three components in each direction. So G is like a tensor kind of creature of this electromagnetic Maxwell operator and how it responds to dipole solutions. And once you have this, then I can take any current source J that I want to, and then through a convolution with G, this will tell me what the electric field as a function of position R and frequency omega is. So this works well in like plasmonic systems because G is something that encodes everything about the material structure, dispersion, and loss. So it is a good candidate of an object to formulate theories in terms of if we want to talk very generally. So now we're going to sort of move towards quantum mechanics. And the question to pose is, how do I quantize the electromagnetic field in sort of any medium of my choosing. In free space, here's an expression for the quantized electromagnetic field operator for the vector potential A. And it's, you've probably seen something like this before, and this is in the Heisenberg picture, so there's a time-dependent phase as well. But it's, an expansion in terms of creation and annihilation operators, and then you get these e to the IKR type plane waves and polarizations, because those are the sort of eigenmodes of Maxwell's equations in normal boring vacuum, and then you just have a free space dispersion, omega equals ck. So if you take a quantum field theory class and you're calculating stuff about like electron photon interactions, or maybe in an AMO class, this would be the sort of formalism that you use to think about the quantized electromagnetic field in vacuum. One level up from this is in a situation which has low loss, so that I can still write an eigenmode expansion. And in this case, we assume that Fn here are eigenmodes of this Maxwell operator. Epsilon is some structure which varies as a function of R, so like a photonic crystal, for example. These modes are normalized in a certain way with epsilon to ensure that every photon has energy h bar omega. So then the vector potential operator in this case can just be written as a sum n over.
So when it says lossless here, and I'm like epsilon is not a function of omega, this is presumably there aren't like polaritons that are excited that could cost you energy by like there's no resonant frequency at which you're exciting.
Yeah, exactly. So like this would be like in silicon or something like that at optical or telecom frequencies, like, in the optical to near IR, where dispersion and consequently loss, since they go hand in hand with each other, are not so important.
Got it.
There's actually a way you can modify this normalization to include like a little bit of dispersion and loss, assuming it's not too extreme. But formally, this, from a formal point of view, this is only good if there's truly no dispersion or loss. And then the final level is in a completely arbitrary environment characterized by a Green's function. And in this case, the vector potential operator takes this form. So G is the Green's function that I mentioned before, which satisfies this equation. And instead of having A's and A daggers, we have these F of R and omega creatures. I'm not going to go into a lot of technical details about this, but the key insight is that in a sort of general in a general medium like this, the vector potential coordinate is no longer a good thing to make creation and annihilation operators for. Instead, you can make creation and annihilation operators for current sources at some position and frequency. So F here, F and F dagger are basically creation and annihilation operators, which create spatially localized and single frequency dipole sources at different spatial parts of the material, which you then have to integrate over. And then by constructing all of those different dipole sources together and convolving them with the Green's function, you achieve your vector potential operator. And now all you need to know is, G and epsilon, which can also be dispersive in a material like this. So this gives you the level from, easiest to most complicated, and I had to do this. So from what we're going to be talking about going forward, this is kind of the framework in which you can assume that under the hood, is being used to describe the situation. So to give an example of what you can get, through this versus with this, I'm going to talk in detail for a minute about spontaneous emission. If you have a single two-level transition between an excited electronic state and a ground electronic state, then you can calculate in free space the spontaneous emission rate, gamma naught, of the system, and it's a pretty simple function of the frequency of the transition, the dipole matrix element that connects these two states, and then fundamental constants. But what we're going to see is that this is not actually necessarily going to be the same if you're in the presence of something like plasmon polaritons or a cavity or something like that. In other words, a fundamental assumption in deriving this equation was that free space electromagnetic field quantization was the way to go. So if you do this calculation using the electric field operator as the sort of generalized version, you can end up with an expression like this, which casts the spontaneous emission rate gamma in terms of the imaginary part of the Green's function evaluated at whatever location your two-level system emitter is at, and at the frequency which is relevant to the transition. And
so
this
should I understand this as like in the cavity there are only certain frequencies allowed, and so I'm restricted here?
Well, the way to think about it here is that because the two-level transition, the two-level transition has some resonant frequency, omega EG, which is set by its energy level spacing. And so as far as the two-level system is concerned, only photons at that frequency are ones that it can couple to and asymptotically and still maintain energy conservation. And so if you're in a system like, a single frequency cavity, then you'd want to tune that to be resonant. But, you could also have a system like a photonic crystal, which does have many different eigenmodes at different frequencies, but then the only one that the emitter sees is the one that's, resonant with its transition.
Got it. Which is why this imaginary Green's function is entering.
Yeah, and the imaginary part here is actually interesting. The imaginary part of the Green's function is basically related to the density of photonic states in the environment. So the higher mg is at some particular frequency, the more different states there are that the emitter can decay into, and consequently, the transition rate will be higher. So an example of this in a cavity, we can write down gamma over gamma naught, which is the free space one, and see by putting in like a two-level system in a cavity how its spontaneous emission rate changes. This n.u thing on the right is just like a spatial mode factor, so it doesn't really matter. The main quantities of importance here are q, which is the quality factor of the cavity, and v over lambda cubed. V is the cavity effective mode volume, and lambda is the wavelength. So what we see here is that if you want to have a large change in the spontaneous emission rate, then you want to have a high quality factor and also a small mode volume. Or in other words, you want to confine the mode down to a level which is ideally smaller than the wavelength of the frequency of light that you're dealing with would normally be if you were in free space. Another thing I'll point out really quickly is that this n.u factor, which determines how the mode overlaps with n, which is like the dipole vector of the emitter, if you were able to fix it into a single direction. If you construct a situation where these things don't overlap, you can also suppress the spontaneous emission rate and create a situation where, the lifetime of an atom ends up being of a transition in a quantum dot or something ends up being much longer as a result of not being able to couple very well to any mode that's in its environment. So this comment on the sub-wavelength nature here is where we're going to kind of call back to these polariton discussions that we had earlier, where I was talking about how people were interested in these things largely due to their high level of confinement, which exactly describes the fact that at a given frequency, their wavelength can be much smaller than it usually would be. For graphene plasmons, the confinement factors that have been observed experimentally are, I think people have gotten like a little over 200. And so you take something, a graphene plasmon, which is usually in the, like near infrared frequency range, which would usually have a micron scale wavelength. And then this thing now has a, tens of nanometers scale wavelength. And so this will effectively allow you to get a much smaller mode volume. Another way to think about this too is how I like to think about the dipole approximation, which is that, from a semi-classical analogy, spontaneous emission of an atom is a lot like an antenna emitting, radiation. And it turns out that atoms are really terrible antennas because the wave function of the atom is on the scale of like angstroms or maybe a nanometer if you're lucky, whereas Even if you're emitting kind of high frequency radiation like ultraviolet, that puts you at like 100 nanometers, which is way bigger. And then if you're emitting something like visible or infrared radiation, that's even way bigger. And then, if you're trying to do it with radio waves, then you're pretty much screwed. So basically, by shrinking the optical wavelength, you're still going to be a lot bigger than the wave function of the emitter, but you can at least put yourself in a situation where it's better. So here's an example of the Purcell factor, which tells you the rate of enhancement compared to a free space transition of a two-level dipole emitter, which is placed over a nanodisk of monolayer hexagonal boron nitride, which supports surface phonon polaritons. And due to the nature of the confinement, if I recall correctly, I think the spontaneous emission rate enhancement actually scales as something like the confinement factor cubed in this case for a dipole transition. So something like, a confinement of 100, if you cube that, you start getting these quite substantially large values of spontaneous emission rate enhancement. So it's not like it goes up by a factor of 5. It's like it's, 8 orders of magnitude faster than it was before, which is really quite striking. So the kind of key takeaway here is that the electromagnetic environment of a two-level atom, for instance, can entirely determine and reshape the way that it interacts with the environment. So in other words, spontaneous emission rate is not in any way something that's intrinsic to the atom itself, but rather is a function of where it's located. I'm going to talk about a really cool application of this, which ties together these ideas of Purcell enhancement and density of states. So this probably looks insane, but basically there's this professor, he's a professor at MIT now, newly in the mechanical engineering department. His name is Ashwin Gopinath, and he is a pioneer in the intriguing field of DNA origami. So the minimal version of this is that he can do something. His group will take DNA strands, generate the DNA strand so that it self-assembles itself into like a triangle. And then they can also put like markers on there so that certain kinds of fluorescent dye molecules, which is what's being shown here, can attach to the DNA strand at points of choice. So this is a fluorescence microscopy image of one of these DNA triangles with these fluorescent dyes, which are fluorescing at these points that have been chosen on the triangle. And this, has a kind of singular resonant frequency that can be accessed. So that's the kind of fluorescence that's being seen here. So then what happens is you take this DNA triangle, which is basically just a way to carry this fluorescent dye molecule for all purposes here, and place it in this photonic crystal cavity. So this also basically has a spatially confined mode, which is resonant with the dye molecule. And depending on where you put it in the cavity, you may have better or worse mode overlap and higher or lower density of states at that specific position. And so thus by moving where the triangle is, which is something that he can magically control, you can essentially change the environment that the dye molecule will see within this cavity. And then because he's a madman, you take one of these cavity triangle fluorescent dye units, and then you make a grid of those that's of macroscopic scale. So you get basically a bunch of pixels, and at each of the pixels, they're able to put the triangle and thus the dye molecule wherever they want in the cavity to have spatial control over the spontaneous emission, or equivalently the fluorescence rate also works in this kind of way. So that then you make your giant silicon wafer and take a picture of all of these wafers, and he was able to construct things like this, where every pixel here is a photonic crystal cavity with a DNA triangle placed specifically where he wanted it, and on that DNA triangle there are dye molecules which are sensing the photonic environment at each of these points.
Okay, this is very cool. Why DNA? Like,
yeah, the purpose, DNA is not important here, or sorry, for the physics, the DNA is not important. In this case, the DNA basically allows them to say like, like I want, this dye molecule, I want you to go here. And then they also have techniques so that they can get the DNA to stick wherever they want to on the photonic crystal cavity. It's basically people know how to manipulate DNA super well.
Got it.
And so you can design these strands that will self-assemble. And the other thing too is that like all of this is self-assembling. So like you pattern, you do some patterning, you do the DNA design, and then you like make like a solution of all this, of all these unfolded strands, and then you like mix it together, and then it makes this.
Wow.
So this, yeah. So
is the information of this image like encoded in the DNAs?
No, well, the information of the image is encoded in where you put the triangle. So like, for example, if you put it in the middle, maybe the fluorescence rate will be very high, but then if you put it off in the corner here, it won't be as high. So at every pixel, the position of the triangle is slid around to map to whatever intensity is desired in the final image.
Okay, I also have to ask, like, what is the potential application here? Because it's really cool. Like every stage of this, I have very little knowledge about. But like, so you make a little screen, but then what do you do with this?
Yeah, I think there are different like, one thing you can do here is like, so one thing is that this is definitely, it's a probe of the photonic density of states. So maybe you have some structure and you want to map out spatially what the photonic density of states is. Oh, the other thing is that these DNA triangles are like 100 nanometers, which means that the spatial precision of like where these emitters goes is like on the orders of tens of nanometers. Which is a level of spatial precision that, because the crazy thing here is that this wafer is like centimeter scale. Wow. And so you're able to get like nanometric placement precision over, macroscopic scales, which is I think largely, which is something that this guy managed to pioneer doing with DNA that other people have been kind of struggling with. The question of like, how do I take a single molecule and orient it exactly where I want it to go is like a very hard problem that people have wanted to solve for a long time.
Mm-hmm.
So this is obviously sort of like a proof of concept illustration. But even just things like many emitter dynamics. Just the ability to put a bunch of different molecules oriented however you want, wherever you want them, is very powerful. So, yeah, so that's cool. I thought this was kind of too cool not to share. So then what I want to move on to now, I think I've kind of, clearly established the principle that, something like spontaneous emission is the example we've dug into so far, is very much influenced by the photonic environment that it's in. And what I want to talk about now is a sort of more unified picture of how all light matter interactions are ultimately subject to these same kinds of consequences in different materials with different structures. So that picture is expressed here. And this, as well as some of the other content, is from a review article written by Nick Rivera and a collaborator of ours that came out last year. So in ordinary quantum electrodynamics, you think about something like an electron-photon interaction, which is described by this vertex. And the unified picture that I want to paint now is that this electron can actually be several different kinds of electrons. It could be a free electron, like a relativistic electron in a scanning electron microscope. It could be a block electron that's bound in a material, or it could be a bound electron that has discrete energy level states, like in a quantum dot, quantum well, some kind of atom. for example. And then on the photon side, instead of just having a boring free space photon, as is described with the usual mode expansion way of thinking about the electromagnetic field, we can have any kind of photon flavored thing that we want, whether it be in free space, a block photon in a photonic crystal that's periodic in a single resonant cavity mode, a polariton like a plasmon, or a phonon in a material. So any bosonic photon flavored excitation will be able to is subject to the same kind of interaction with electrons. And so now, with that perspective in mind, we can just kind of start drawing stuff. And many of these processes correspond to things that have their own names and are often thought of as, different physical processes. But for example, here's a bunch of examples of things that are all basically single photon spontaneous emission. And highlighted here are the examples that I talked about so far. But then on the right-hand side, if the electron that you're thinking about is not, say, a two-level system electron, but rather a different kind of electron, like a free electron, then if you have a free electron which is moving in some homogeneous medium, if it's moving fast enough, it can emit radiation through the Cherenkov effect. Now, with this particular example, the Cherenkov effect is something that can be described entirely basically in terms of classical electrodynamics, and quantum corrections are not super important. But from a quantum mechanical perspective, the Cherenkov effect is basically just spontaneous emission, except it's a free electron that's doing that spontaneous emission. So a lot of these things here can kind of be described semi-classically. What gets more impossible to describe semi-classically are multi-photon and higher order processes, which I will intimidate you with briefly here. So for example, something we're going to talk about in a sec here is two-photon spontaneous emission, where you have an electron which relaxes and emits two photons in the process. Other important ones here are things like the Lamb shift, so energy level shifts that are caused by self-interaction with the electromagnetic field. And then down here are like higher order, potentially non-perturbative processes where you send very strong fields at a system, causing it to absorb to absorb dozens of photons and then emit a single photon, which is all of those photon energies summed together. So this, this is an extremely nonlinear land. But essentially, the point here is that any light matter interaction process you would want to think of can be thought about in this kind of framework. And once you have the formalism for quantizing the electromagnetic field in any system you want, then you can kind of go to town. So for the last handful of minutes here, I'll just talk about a couple of examples that I haven't touched on yet. One is that of two-photon spontaneous emission. So this is a thing that actually does happen. If you have a two-level system, you can easily compute its rate of dipole spontaneous emission by the emission of a single photon, which is resonant with the energy level transition. However, if you go to second order in perturbation theory, you can also look at processes where two photons are emitted, and the only constraint now is that their two energies sum up to the resonance energy. And as a result, you end up with a continuum of different frequencies that are emitted as opposed to being restricted to a single resonance. Now, this actually happens in hydrogen, for example. The 2p to 1s transition is a normal dipole allowed transition, and its lifetime is on the order of like 50 nanoseconds or something like that. It's somewhere around the order of nanoseconds. And so that's a normal fast-ish transition by atomic timescales. The 2s to 1s transition in hydrogen is parity and dipole forbidden, which means that you cannot make that transition by the emission of a single photon for symmetry reasons. But if you experimentally prepare the hydrogen atom in the 2s state, then it will relax back down to the 1s state. And two-photon spontaneous emission is actually the mechanism by which this occurs. And the lifetime of the 2s state, as dictated by this process, is something like a tenth of a second. So on atomic time scales, this is basically forever. And this is to be expected since this is at second order in perturbation theory, and thus this is quite slow normally. However, we can play the same kind of trick that we did with single photon spontaneous emission by taking a atom or a two-level system, quantum dot, whatever it is, and placing it in the vicinity of something that has like highly confined surface polaritons, for example. And when you do this, you'll find that depending on how close the atom is to the surface so that it can, couple either more or less effectively, you'll find that the spontaneous emission rate can be enhanced by absurd amounts. And it depends on the distance to the surface h. So once you're very close, it'll be enhanced quite a lot. Though at those super tiny distances, things like spatial non-locality of the conductivity of the material also becomes relevant. Anyway, so that's an example of a two-photon process. I'll also talk briefly about processes involving free electrons. So one example of this, you can think about a sheet of graphene, and the relevant, surface polariton modes in this case are the graphene plasmons, as I mentioned a bit earlier. And then, one thing you could do would be to like take an electron beam and shoot it above the surface and look at the Cherenkov radiation into the plasmons. However, it turns out that there's been some theoretical study, this was in our group before I was around here, about very fast electrons in the graphene itself, which are able to do this process. So you have some hot carrier in the graphene, and then this carrier is actually going a bit faster, or moderately faster than the phase velocity of the plasmons in that material, because plasmons are kind of slow. And as a result, you could get, you could imagine having generation of plasmons through this kind of Cherenkov process. Something that's at higher order, or that's at second order instead of first order, would be taking an electron beam, shooting it above the surface of a material like graphene or something else that has confined polaritons. It really doesn't matter what it is. And then looking at two photon spontaneous emission processes from this free electron, so that the electron emits two things. One of them is something like the polariton into the surface, so it could be a plasmon. And then the other thing would be a higher frequency photon into free space. And so you would have a pair generation of photons where one of them is like an infrared plasmon, and then the other one is like an ultraviolet frequency photon that goes off into the distance. Now, you could think about like, sending an electron through a medium with an index of refraction and asking, what the two photon pair generation would be at higher frequencies, but this would be absurdly low. And so in this case, the kind of absurdly low nature of this process gets helped by the fact that you have this sub-wavelength plasmon as part of the process, so that the generation of the ultraviolet or X-ray frequency photon, which is probably what you care about, could be is kind of, it piggybacks on the efficiency of this process. And the amount that you get out theoretically when you do something like this, it's not a lot, but it's like way more than you would expect normally, and it's maybe detectable. One final example is with this sort of free electron stuff on this slide, is a higher order kind of process where the picture here is that you have a free electron beam going over a plasmonic surface. Then you send in a super strong pulse of light at some lower frequency. And then as a result, you could think semi-classically about the electron wiggling around and acting as a current source. And then plasmons can be emitted either at the incoming frequency or also potentially at several or many harmonics of the frequency that was coming in. So in this sense, the free electron is acting as a nonlinear converter, which under the presence of sufficiently high driving fields will create many harmonics of that driving field in the form of plasmons at different frequencies. So a platform that people are starting to use to explore these kinds of free electron interactions are scanning electron microscope or transmission electron microscope setups. with electron energy loss spectroscopy, also known as EELS detectors. The setup here is basically that you have a electron beam, which has a ultraviolet pulse sent at it, and this causes the basically on-demand controlled emission of an electron bunch from the source in the TEM. And then this is incident at some sample that has some kind of optical structure in it. And then you also send resonant laser pulse in. And the way you do this is so that you basically do this so that the electron pulse and the optical beam hit each other at basically the same time, or with a slight temporal offset on the order of picoseconds. What happens now is that the cavity, or you say it's a cavity, gets populated with photons of a single frequency, and then the electron beam goes by. And because the fields are strong, the electron beam can either spontaneously emit a bunch of photons or one photon, or it can absorb some of the photons that are already in the cavity. And what this means is that when you take the electron beam and you send it down to the electron spectrometer, you'll find that the electron energies show up in basically a comb kind of shape, which are spaced by integer amounts, which are spaced in integer amounts that are equal to the photon energy. So you can say, this particular electron had a net gain or a net loss of this many photons. So these sorts of experiments are cool because it's not very often that we get to count photons in this kind of sense and, see, yes, they really are quantized. Yes, you can really, have the electron absorb 7 photons. One application of this that's been done is using it for imaging. So basically, a lot of information about the mode itself, the electromagnetic modes themselves, is contained in this electron energy loss spectrum, especially when you're, when you do things like time delays. So this here is a result from a recent paper by a colleague of ours who has one of these fancy transmission electron microscope setups. And they took a photonic crystal slab and sent the electron beam at it at different with different incident frequencies and also different angles of the photonic crystal slab. And as a result, and by analyzing the data of the electron energy loss spectroscopy, they were able to reconstruct both the band structure of the photonic crystal slab, as well as make real space images of the photonic crystal modes, which are basically the block modes in the material. So in this kind of setup, we're able to see processes which involve the emission or the absorption of many photons, as a single process, which is a kind of higher order thing. And this is possible in this case because the electron beam and also the optical excitations involved are quite strong. So this effectively increases the coupling strength, allowing you to get to higher order processes. An ultimate limit of this kind of thinking, though, is what happens when the coupling between light and matter are very strong, even in the absence of any applied fields. And this is what people think about who study sort of strong and ultra strong coupling physics. As a quick example and framework for thinking about it, this is just the Rabi Hamiltonian. So we have a 2-level system, which is coupled resonantly or near resonantly to a single electromagnetic mode through a dipole coupling to the electric field. And usually commonly we're in the weak coupling regime, where this coupling parameter G here can be considered to be quite small compared to omega naught, or the relevant resonant frequencies. However, if this starts to get bigger, then when you solve for the eigenstates of this Hamiltonian, you'll find that you get Rabi splitting, and you get splitting of what used to be 2 degenerate states into 2 non-degenerate states. So there are experiments that have been done that essentially put an atom in an extremely tiny cavity, and the cavity is small enough that the effective coupling parameter becomes sufficiently large that you can observe this kind of Rabi splitting by then sending in an additional weak probe and mapping out the resonances. A really cool application of this is in a field that's been developing in the last 5 years, which people are calling QED chemistry. So what this example on the left essentially shows us is that the eigenstates of the system actually start to hybridize with the photonic states of the system. In other words, if I'm in the weak coupling regime, I can take an atom and put it in a cavity, and I don't have to think about the cavity changing the nature of the atom. But when you're in something like the ultra strong coupling regime, where the coupling parameter becomes comparable to the resonant frequency itself, then you end up in a situation where it's no longer good to think about, the atom being in the cavity. The atom and the cavity are their own sort of cohesive system. What this means is that if I take some kind of chemical reactant whose reactivity properties and other chemical properties are dictated by its energy level structure, and then I manage to strongly couple that to some cavity mode, the energy levels can change, and thus so can its chemical properties. So these are some crazy experiments that have been done in the last handful of years, where basically this group took some chemical reaction, characterized its reactivity rates and other thermodynamic chemical reaction parameters, and then they did the same experiments except in a silver microcavity, and they're actually quite different. And I know this guy had quite the time trying to get this stuff to go over with the chemistry community, because this basically sounds like alchemy if you don't know how quantum electrodynamical strong coupling works. But the point of this is that, and as I'm coming to the conclusion of my talk, the main point here is that the photonic environment of light matter interactions can completely reshape the way that everything that we think about works, ranging from weak coupling physics like spontaneous emission to strongly driven electron systems to the ultimate limit in which even ground state properties with no photons involved at all can change the way that light and matter interact with each other. And so as I conclude my talk, I just want to talk a little bit about what's to come and what some interesting applications for all of this as a whole are. One is that people want to create efficient and controllable sources of light, both classical and quantum light. And as you're able to gain better control over this, you can start to improve the way that we're able to image and sense systems at different frequencies. Another clear example of applications is in either classical or quantum optical computing. And the ability to have a strong degree of control over things like memory, or the way that operations can be implemented optically. Not listed here, but something that's important too is that people are interested in low loss plasmonics. So plasmons can be, on one hand, really great because of their sub-wavelength nature. On the other hand, they're super lossy, and for optical communication, we'd like to be able to propagate something in a fiber across the Atlantic Ocean like we can with silicon, which is virtually lossless at optical frequencies. On the other hand, graphene plasmons have a wavelength of 50 nanometers and a quality factor of 200, so you're not getting very far, let alone across the Atlantic Ocean. So from a materials and condensed matter standpoint, people are very interested in looking for materials that can rise up to these challenges. And then, in terms of strong coupling physics, where people are interested in how, strong and ultra strong coupling can alter materials properties as ways to change the fundamental properties of materials for applications. And then all of these concepts can also potentially be used towards designing light sources like lasers, for example, at frequencies which are usually hard to make lasers at, or creating lasers with quantum statistics that are beyond those of a coherent state, which a normal laser creates. So these are all examples of things that we tend to think about. And with that, I believe I conclude my talk and can take any questions.
Thank you. That was great.
Glad to hear it.
I am interested. So you mentioned eels as a measurement.
Yeah.
And there's this paper. I don't know if you're Peter Abamonte's group at UIUC.
Oh, I feel like I've heard this. I feel like I've heard this name.
Yeah, he does something. It's been on my radar that when I finish my current project, sometime in the midterm, I'd like to take a look at it. But he does this thing which is called M-eels. So I don't know if you know anything. It's momentum resolved. So I guess
interesting.
scanning through like maybe your detector where you have this electron and light source that are coming together, your detector is scanning in momentum space.
I see.
As well. Yeah, okay.
Any other questions?
Yeah, I have a question about the QED chemistry. Is the idea like artificial molecules or quantum dots?
That's one thing you could potentially apply the concept to. In this case, I think they're just taking something that you would normally consider to be like a regular reagent in chemistry, and then you do the reaction on your desk, and then you do that same reaction, but between two silver plates that act as a cavity, and the results you get end up being different.
The scale of the cavity is small, like close to the molecule scale, right?
It's probably on the like tens of microns scale, if I had to guess.
Sounds cool.
Yeah, I know this guy that does this stuff has been accused of alchemy, because that's sort of what it sounds like. It's a little bit upsetting initially that, you know, taking a chemical reaction and putting it in a metal box can change how the chemical reaction works. Also, just to emphasize in case it wasn't clear, there's no light applied here. It's all just ground state. Any last questions?
I'm super curious to hear more about this DNA thing.
Yeah,
that's so. It's like Rube Goldbergian in the like levels of stuff that is stacked together.
About a year. So yeah, this guy, he was like a research scientist at Caltech for a number of years while he was developing this. And then he was like newly hired as an MIT professor by the MECI department sometime like early last year. Or maybe like late 2019. And Marin and I and a couple of other grad students from our group had a meeting with him like early 2020, where he was like explaining all of this stuff to us, and all of us were just like sitting there with our jaws on the floor the whole time.
Yeah, I think that would be
it was a yeah, the what's it called? Yeah, he's a very excited person, and it just kept like, there just kept being more like, but wait, there's more kind of stuff. Something that I didn't even show here that he did was they're able to also control like the orientation of the molecule. So you can like change the orientation of the dipole moment within the thing. So in a new paper, in a newer piece of work, they made like a polarization sensitive kind of thing, so that like their image was like an almost compass shaped thing, and then like if the light was at one polarization, it would, you know, light up the arrow this way, and if it was at the other polarization, it would light up the other way. And I think they even did something crazy like, you know, making like a they started doing things where it's like two different paintings depending on what polarization you illuminate it with.
Wow.
Yeah, this
that
guy's
sounds so
this guy's a mad scientist.
All right. If there are no other questions, thank you, Jameson. That was great.
If anyone has any feedback on parts that were either particularly good or confusing or something like that, that's also welcome, as I suspect this may, be a talk that I give in other contexts.
Let's see. Maybe I think what could have had more elaboration is like the beginning where you were talking about those like trapped plasmonic modes on the edge of the system.
Trapped plasmonic modes.
I mean, so like they don't penetrate very far into the 2D systems. Yeah, like this lambda naught. So like some more explanation maybe about that.
Yeah, I see. Yeah.
But I think I guess maybe I took AMO with Wolfgang, and so the cavity stuff was very clear for me.
Oh, good.
That maybe not for others.
Yeah, I think this was also like I feel like I'm like pushing the borderline of what you can fit into an hour. Because on one hand, I mean, I tried to, maintain some coherent idea. Part of me was wondering if I should have maybe showed this earlier.
I think it was pretty helpful to clarify, although
I ultimately decided to go with like showing the few simple Purcell enhancement examples.
I think that's a good decision.
Before introducing the sort of broader framework.
Yeah, in college, I took an analysis class from this guy, Wilhelm Schlag, who is like mechanical with his lectures. And he always went easy, specific example, broad theory, tie it back to easy example, and then show the utility of the theory. And this, I think, was in that structure.
That was the goal. All right. Well, yeah, I mean, feel free to ask any other questions. Also, if anyone has, additional questions offline or something, or if there's, specific subtopics of this that people would be interested in hearing about, like more in depth, whether it be specific physical systems or like, seeing what's it called? Seeing more about like the general mathematical formalism that underlies some of this stuff, and like, something more along the lines of like, how do you compute stuff? That's also, fair game. I figured that was the wrong approach for a first talk.
Yeah. In the midterm, I may reach out to you about eels just to get some sense. Cool.
All right. Well, thanks everyone for coming.
See you.